Hi, my name is Nicholas Torres, and I am the project manager for the Arecibo Observatory Radiation Pattern Measuring Drone Project. With me are Jamil Gonzalez, Pedro Gonzalez, and Adrian Rivera, and we will be talking about our latest progress with the project. The Arecibo Observatory is the second largest radio telescope on the planet, with a diameter of 305 meters on a spherical dish with low operating frequencies of 5 and 8 MHz. This is a unique structure capable of performing specific experiments. At the center of the dish there are 6 dipole antennas that produce a circularly polarized directed magnetic field. This is called the heating facility. Antenna characterization is a common test performed to observe how an antenna operates experimentally. Far-field measurements are performed in housed anechoic chambers to validate antenna operations. The distance for far-field measurements is approximately 3 kilometers from the dish. Because of Arecibo Observatory's fixed structure, this means 3 kilometers above the structure. Because of the size and frequency of operation, it is hard to validate its operation. When far-field measurements are not a viable option, we can use near-field measurements and use the fast Fourier transform to predict a far-field pattern. From the equations below, we can obtain far-field and near-field distances. The region of the near field is below 400 meters. Near-field measurements are performed using a grid pattern. With some equations, we can obtain the size and coordinates to sample an antenna according to the frequency and size. One reference states that the optimal distance for recording near-field measurements is 3 lambda. In this case, that is 180 meters from the antenna. In this figure, we have our sampling grid and dimensions. The next shows an example of experimental data, and the last is a 3D model of the same experimental data.
Our system, the Phoenix, is composed of the following parts: RTK GPS, the parachute system, single-board computer, a camera, the microstrip antenna, and the software-defined radio. Hi, my name is Jamil Gonzalez, and I will be continuing the presentation. Let's talk a little bit about the drone system diagram. The process begins when the Arecibo Observatory heating facility irradiates the 5 MHz signal into the air. Our antenna will measure the magnetic field and convert it into an analog electrical signal. Next, the matching circuit conditions the signal to be sampled. We use an converter to increase the frequency of the signal. After it, the signal enters to our ADC, in our case the software-defined radio, or SDR. From there, we perform IQ computation to obtain the magnitude and phase of the signal. The data is stored into the single-board computer, or SBC. The SBC also contains the autonomous flight software, and it sends commands and coordinates to the flight controller. The flight controller uses a GPS to move the drone and subsystems into the appropriate location where we will capture data. The flight controller also has a parachute ready to launch in case any accident. Lastly, we use a camera on our drone to monitor the flight.
On this detailed diagram of the microstrip Minder antenna system, we can see how the signal will travel through the components once it receives the signal from the heating facility. The first component that will encounter the signal will be the balloon transformer that will unbalance the signal. Then it will pass through the matching circuit where it will be attenuated and matched to eliminate any signal reflection. Finally, it will pass through the up converters to convert the signal into higher frequency so that it can be read by the SDR. The main purpose of the matching circuit is to obtain maximum power transfer to ensure the safety of the components of the system from any reflection. It was decided to run some tests in the impedance of the antenna and the return loss of the components. The impedance that was expected was of 50 ohms, and the results of both polarizations and frequency was approximately 49.4 ohms. The return loss expected was of 50 dB, and the results obtained from both polarizations was of 43.7 dB. There are some margin of error, but we can conclude that the antenna's components are serving their purpose. Here we can see the physical appearance of the antenna system. Now we will move on to the GPS.
The real-time kinematic GPS is a common land surveying tool. With modern versions of this equipment, we can mount the system on a drone and obtain centimeter-level precision. Typical GPS use georeferencing to provide data on a location. We can also extract the timestamp of the measurement to allow us to further synchronize our data. And with the use of a reference point, we can increase the precision of our measurements. In the figure below, we have a picture of how this implementation is performed. It consists of a rover and a base module that communicate with each other, each with their own satellite antenna for increased precision.
This is the near field measurement data flow diagram. First of all, the drone is going to go to a specific location on the dish, where then the Python script is going to be reading data from the SDR. The SDR reads the IQ data from the dish and outputs it in binary. Therefore, the Python script is going to parse that data, where the first 32 bits are the real part of the value at the location, and the next 32 bits are the complex part of that number. And then it's going to create a binary file with those values of x and y, and it's also going to create a text file with the GPS data for the current location. And it's going to do this several times. For later on, the MATLAB script can get those values at the same location and then average them. So after we do multiple runs at that certain location, it's going to go to another location. It's going to do it again for that location. So then after we gather all this data, it's going to be saved onto the onboard computer, and then with that data, it can be later retrieved for a MATLAB script to be able to calculate the average of each complex value of each location. And then with that average value of each location, it can get the magnitude and phase. And after it calculates all those values, it will save those values into a text file where it will contain a table of all the values.
In conclusion, testing will be done in the laboratory environment instead of the Arecibo Observatory due to recent developments on the site. Validation of the antenna has yielded positive results. This helps us confirm measurement data is correctly conditioned. And a new RTK system will be purchased, one capable of reaching opposite ends of the sampling grid without losing communications with rover and base modules. Thanks for listening to our progress presentation.